Hi, my name is Lucas Collins. I'm a rising sophomore here at UNC, and I'm applying to be a peer mentor for the upcoming 2018 spring term. I would like to peer mentor for Chemistry 102, which is a class that I took along with its lab in the fall 2018 semester with Dr. Bleem. A couple things about myself. I am a huge sports fan, and I'm from Charlotte, North Carolina. Those two things going together. I'm a huge Panthers fan and also a massive Hornets fan. I've always loved sports, played soccer in high school, played basketball in high school, and I've continued those at the intramural level here at UNC. I'm a huge dog lover as well. Can't wait to get one of those when I'm older eventually. Family dog is a Great Pyrenees named Lily. That's about it. So let's see. So why do I want to be a peer mentor? So there's two main reasons. The first one being that peer mentoring was such a great help for me during my first year at Carolina. I learned so much from the peer mentors, not only the material, but I learned a lot about the nuances of college and also the nuances of certain courses. So they're saying, oh, well, you should study this more, don't study this as much, or maybe look at this, hey, look at this, maybe that. So you just learn a lot of new things from peer mentors, as well as knowing they've been through a course, they've been through this experience already, so they can really help you, and they're really beneficial in that way, and I would love to be able to pass it on to upcoming first years or sophomores or juniors that are taking this 102 course. Another reason is that I am pursuing my MD PhD, and this would be a really great experience for me just to learn how to teach others. I've done it before at the high school level, but not really at the college level, so it would be a really cool experience for me. With that being said, let's just jump right into the problem. So here it is. The problem reads, a mixture of SO2, O2, and SO3 at 1000 Kelvin contains the gases at the following concentrations. SO2 equals 5.0 times 10 to the negative 5th molar. O2 equals 1.9 times 10 to the negative 3rd molar, and SO3 equals 6.9 times 10 to the negative 3rd molar. Is the reaction at equilibrium? If not, which way will it proceed to reach equilibrium? And then you're given the equilibrium constant of Kc equals 0.0125, and you're given the reaction equation right here. Okay, so what you're going to have to do in this situation is you're going to have to compare your K to your Q. So how do you find your Q? You find your Q the exact same way as that you find your K. So let's find our K, and then we should see how we find our Q. Okay, so let's find K. So we already have K. We have the value of Kc equals 0.0125. Let's write the expression down so we can later find Q. Okay, so the expression down, so it's going to be products over reactants, only gases, no solids, no liquids. Here we only have gases, so it works out. Don't forget these coefficients are going to be used as exponents in your equilibrium constant expression. So let's write it out. So it's SO3 squared over SO2 squared and O2. Okay, so here's our equilibrium constant expression. So we can use this exact equation right here to find our Q value. Okay, so our Q is basically our reaction quotient. That's what it's called. So what it tells you is if a reaction is at equilibrium or which way it needs to shift, either towards the reactants or towards the products to reach equilibrium. So to know that, you're going to compare your Q value and your K. We already have K, so let's find Q. So here we are, we have this equation right here. We just need to plug in values. So where do we get these values? From the problem. They're already given to us right here. So this is at a random point. It may be at equilibrium, it may not be. So it's up to us to find out. Okay, so let's figure it out. Let's plug it in. So SO3 is given to us at 6.9 times 10 to the negative 3rd. And that's still going to be squared. And then SO2 is going to be 5.0 times 10 to the negative 5th. That's still going to be squared. And O2 is going to be 1.9 times 10 to the negative 3rd. Okay, so if you plug that into your calculator, just numbers, so just plug it into your calculator, find it, you get about 991.9. Okay, obviously far larger than K, so what does that tell us? Okay, so we have three real options. You could have Q being greater than K. If Q is greater than K, what do you need to do? You need to move towards the reactant side to be able to reach K. That's just because this is so large. If we add more reactants, this is going to decrease in size, and eventually this will be equal to your Kc. So that's what you need to do. You need to add more reactants. Okay? All right, so now what about if Q is equal to K? Well, you don't need to do anything. It's already at equilibrium, but we don't have this obviously here. And then your third option is going to be Q being less than K. So if Q is less than K, what you're going to need to do is move towards the product side because you want this numerator to increase. You want this guy to go up, so you need that to raise up, so you need to shift to the right. Okay, so which of these three situations do we have here? Let's compare the Q and the K. 991.9 is your Q. Your K is 0.0125. So obviously this is far larger. So Q is far larger than K, so we have this situation right exactly here, which means that you're going to shift towards the left or towards the reactant side. So your answer is no. Is the reaction at equilibrium? No, it's not at equilibrium. If not, which way will it proceed? Well, because our Q is greater than K, the reaction is going to proceed to the left or towards the reactant side, and eventually it will reach equilibrium. Thank you again. My name is Lucas Collins. That's about it for this question, and thank you again.